Ideal versus Real Gases by Autumn Bell and Irene O.
The term ideal gas is probably most recognizable from the ideal gas law, PV equals nRT. The ideal gas law is comprised of Charles' law, Boyle's law, and Gay-Lussac's law. Charles' law is volume and temperature, Boyle's law is pressure and volume, Gay-Lussac's law is pressure and temperature. The R value in the ideal gas law is the universal gas constant. The kinetic molecular theory makes two fundamental assumptions about the properties of gas particles themselves. Gases have no volume, and they exhibit no attractive or repulsive forces. These two assumptions define an ideal gas. They work quite well since gas particles are often widely separated, and what little volume they have is relatively unimportant. This wide separation allows for some real gases to closely resemble ideal gases as they experience weak intermolecular forces. When a real gas is cooled or compressed, the distance between the particles decreases significantly, and these real volumes and forces can no longer be ignored. In 1873, Dutch theoretical physicist and thermodynamicist Johannes van der Waals developed a modification of the ideal gas law to deal with the non-ideal behavior of real gases. He reasoned that if the gas particles each occupied some volume, there would be a net decrease in the useful volume inside an insulated container. Knowing that a decrease in volume had to be proportional to the moles of gas present, van der Waals modified the volume term into V minus NB, where B is a proportionality constant. While evaluating the effect of intermolecular attractions, he also reasoned that if gas particles attracted each other, they would have curved paths and therefore would take longer to collide with the container walls. The result would be a decreased collision frequency and a lower pressure for the real gas than the pressure of an ideal gas under the same conditions. After many observations, van der Waals came up with a correction factor for the pressure with proportionality constant A. Combining his two modifications, he wrote a new equation for the properties of real gases, which is commonly known as the van der Waals equation today. But what do proportionality constants A and B really represent? Proportionality constant A represents the relative strength of attractive forces between the gas molecule with larger values, indicating stronger attractive forces such as dipole-dipole attractions. Proportionality constant B represents the relative size of the gas molecule. The larger the value B, the larger the size of the molecule. Despite properties of ZEF and atomic shielding, the size of gas molecules do not vary greatly from one molecule to another. Attractive forces, on the other hand, vary tremendously depending on molecular polarity and contribute the most to deviations from the ideal gas law.